This video is the first in a three-part series that looks at how to do block-based digital signal processing, and the end result will be a flanger written in MATLAB. We will start with looking at how to add an echo to a signal, and we will do this by processing the signal all at once, so it's very straightforward. Then we look how to convert this into a block-based processing approach. First we do it the naive way in C, so we just focus on the signal processing aspect of how to do block processing. Then the rest of the presentation will look at how to make it more elegant in C than in C++, because this leads up to how it's done in MATLAB using system objects. MATLAB uses an object-oriented approach, and this is what is done in C++ by using classes, but what's actually happening behind the scenes is just using structs in C. Therefore these things are connected, and this is the logical order of presentation. The signal processing algorithm is very straightforward. Our input signal x of k is sent to the output along with a delayed version of it. Alpha is the amplitude of the delayed version, and d, an integer, specifies the delay. We will be assuming throughout that d is greater than 0. When programming in C, we have to worry about where variables are stored. This is especially so when programming DSP chips and memory might be limited. We are going to be processing a block of data. Input data comes in, we add an echo, we send it to the output data buffer, and so we need to know where exactly this data is going to be stored. The function doing the processing, our echo routine, should not have to worry about where to store the output. There are some alternatives that we can follow. One might be that the function doing the processing actually allocates memory to store the answer in, but that means that it returns a pointer to some data that has been allocated, and whoever called our routine should eventually free up that memory to avoid memory leaks. An alternative is for our function to have a static buffer that it can use to return to the user, but this sets an upper limit on the size of the data that our function can handle. So often a good solution is for the caller to pass in both the input data and the output data buffers. We therefore end up with this function. This is not block-based processing. This processes everything at once. Our input is going to be an array of floating point numbers. There are going to be capital N elements in our array. We are told the amplitude and the delay that we want to add, and we will return the answer into the array pointed to by out. In this way, remember, the person calling our function tells us where to put the answer. We don't have to worry about memory allocation. Processing the data is straightforward. In fact, it's almost trivial. Most of the time, we just copy the mathematical formula that we had. The output at time I is equal to the input at time I, plus or minus, whatever your convention is, alpha times the delayed version of the input. The only need for consideration is what happens when I minus d is negative. Well, this happens at the very start. So if our input sequence is 2, 1, 3, 4, of course they're normally floating point numbers, not integers, but if this is the start of our input sequence, when we go to add a delay to 2, we have to add on alpha times something in the past. Well, convention dictates that we just assume that the input signal is 0 for time t less than 0. Therefore, in that case, if we near the start and we have to add something that belongs to the past, time -1, -2, etc., then we just assume that at negative times the input is 0 and the output is just the input, and this extra term here we treat as being 0. We just remind ourselves that in C, arrays start at index 0, and in particular, if we have got an n element array, then its indices go from 0 to n minus 1. Also, as stated on the last slide, we take the input to be 0 at negative times. That's why we had an if statement. So why might we want to do block-based processing? Imagine we had a 10 gigabyte audio file that we wanted to add an echo to. If we used our current algorithm, we'd have to read in the whole 10 gigabyte audio file into our memory. And we'd also have to allocate another 10 gigabytes of memory to store the output of our echo routine. So we're using 20 gigabytes of memory just to add a simple echo to our data. This is a waste of resources. It also is not going to be helpful if you wanted to listen to the delayed sound in real time. You might be watching a video and wanting to add some audio effects while watching it. There's absolutely no reason why we should read in the whole data at once. Underlying block-based processing is the fact that many signal processing algorithms do not need to access the whole data just to compute y of k for a fixed k. For our echo, if we want to find y of 10, and depending on what we've set our amplitude and delay to, if our delay is just 2, then to compute y of 10, all we need to know is x of 10 and x of 8. We don't have to know x at 2 million in the future or x at 0 in the past. We just need to know a small range of x values to get the current y value. The way to think about this is to consider our input streams of numbers. They don't have to be in order, they don't have to be integers, but we've got a stream of input numbers, x0, x of 1, etc. Our output y, if we want to know y at time 0, 1, 2, 3, we just have to know what's happening, in the case that delay is equal to 2, in this little region here. Once I've computed y of 3, I now want to compute y of 4, and this window here just slides over, and so now to compute y at time 4, I just have to know the data inside this little block here. So the way to think of block-based processing is that we are sliding a window over our data. The computation that we do at this time depends on the input in this sliding window here. And as we go to compute the next output value, we slide the window across by 1, and that enables us to do the same type of processing to get the result that we want. Before we try to implement our block-based echo, let's see how it might be used. So here is a main function in C. Remember that we have to allocate memory. So here I am allocating memory to store the input block and memory to store the output block. I need to open my input file, let us say, and maybe I want to store the result to a file too, so I open that as well. Now the actual reading and writing of data from files is a little bit tricky because we need to store floating point numbers. In a file, the basic element of a file is a byte or 8 bits. A floating point number might be 32 bits, and so it's not a simple matter of just reading a byte and we get a floating point number. Rather, we need to read 4 bytes and somehow convert that into a floating point number. Those 4 bytes are going to somehow encode the sign, the mantissa, and the exponent of our floating point number. We don't really need to know that. The other thing that we don't really need to know is that if we've got a data file containing audio data, normally at the start of the file there's what's known as a header, some pieces of information that tell us about the audio data, such as what is the sampling rate, how many channels there are, and so forth. For this reason, I'm just going to assume that someone else has written the functions to read data from a file and write data to a file. And these are the functions read block and write block. Intuitively, read block is going to read in the next 1024 bytes from our input file and store it into our input buffer that we have allocated up here. Write block is going to write to our output file the processed data that has been stored by our echo routine into out block, and it's going to write 1024 bytes. So we are going to be processing the audio stream in blocks of 1024 bytes in this example. The real processing happens here. Our echo function, which is what we have to write, takes in one block of data, 1024 bytes, adds an echo to it, and stores the answer into the output buffer that we have passed to it. And we tell it that these buffers contain 1024 bytes. Now for echo to work, it has to know several things. It needs to know what's the amplitude and the delay, and so we set it up here. But we also have to, it also has to remember somehow the previous data. Because when we add an echo, then sometimes the output is going to depend on the past, and the past might have occurred before this block of data. So I need to remember the past, which we'll elaborate on presently. So a quick summary. We need to write our own read block, write block, and echo. Reading and writing of files is not something I'm worried about at the moment, so we're going to focus on echo instead. We care about the echo function. We can't just use our previous echo function that processed everything at once, because as we said, when we come to computing the output at time k, we need to know x of k and x of k minus d. And x of k minus d might happen to belong to the previous block and not the current block. So our echo function somehow needs to have access to what was previously given to it and not what was currently given to it. And we're going to explore this issue first and see how we can do this in C. For the moment at least, our main consideration is how can I repeatedly call my echo function but have it remember information from previous calls. Now there are different ways of doing this, and they have got advantages and disadvantages. For the sake of being comprehensive, and for the sake of understanding why MATLAB does it in the object-oriented way, I'm going to cover these standard ways of doing it. The first two have got disadvantages. The third one is what's normally done, although it is a little bit more complicated. Not too much, just a tiny bit more complicated. Perhaps the most basic way is to use a global variable. And I'm not going to be doing echo for the moment. I'm going to be doing something even simpler, so I can just focus on one principle at a time. The current principle we're focusing on is how can I call a function but have it remember previous values that was passed to it or that it was using. So we're going to implement a very simple counter. The way we use it is that I first initialize my counter, and then every time I call increment, I want it to return first 1, then 2, then 3. So somehow my function increment has to have memory. It has to remember something from the past. Our echo function is going to have to remember past input to it, so that's why this is relevant. Solving it using a global variable is straightforward. I just declare a global variable right here, integer count. My initialization function sets count to 0, and my increment function just increments the global variable and returns that. So this is straightforward, but global variables are normally considered bad things. Not only do global variables pollute the namespace and might cause some problems if you're using many different files in a large project, but we're limited to having just a single counter. I can't have 3 different counters in 3 different parts of my program because the counter routine I wrote uses a single global variable. For completeness, and because it is a nice trick to know, and because sometimes it is done in certain situations, we can achieve the same thing by using what's known as a static variable. So this is a special keyword in C, which in this case means that this variable here, while you might think it's just local to the function increment, well, it is local, only increment can access it. But unlike a usual local variable that gets destroyed when you leave the function, because it's declared static, it will exist for the lifetime of the program. The way you initialize a static variable normally is by using the equal sign to initialize it at compile time. And so this code will achieve the same thing as the previous code did, but because count is local to increment, it is not going to pollute the namespace. It suffers from the same disadvantage that I can have only just a single counter, and it's also a bit tricky if I wanted to initialize my counter to 5 instead of 0, for example. Because the count value is hidden away inside the function, it's hard to initialize it. I'd have to do some sort of trick of passing an initialization value to the increment function, etc. A little bit messy. Here we have the preferred way. Yes, there's more lines of code, but it's much more flexible and works very well. In fact, if you look at, you look at the source code for Linux, which is largely written in C, and you'll find this trick used everywhere. This is the standard way of passing information around to functions that need it. So we've got our usual includes here. I'll come back to that later. Here's the key part. We're going to create a struct. This is just an umbrella or a container for storing one or more variables. In our case, I only have got a single variable to store, but the key point is if I needed to store more variables, I could add them after here. I could have a floating point number, I could have other integers, I could have arrays, I can have whatever I like. I create this structure and I give it a name, private data. So typedef here is just a nice way of giving this structure a name. It's the old-fashioned approach anyway. What happens in the main program is that I need to allocate the memory here. So I'm going to create data that is required by my counter. I'm then going to call the initialization routine and pass to it the address of the private data that this routine needs in order to do its job. When I'm finished with it, it's good practice to call the release function that we also need to write to get rid of the data. In our case, there's nothing to release, but when we get to echo, we're going to have an array stored in here that is allocated using malloc, and then we need to free it at the end. So the basic structure, and you'll see this everywhere, is you create the data structure needed, you initialize it, you use it, and then you release it at the end. When writing the code this way, and I must have changed the code without changing this, you need to be passing the address of P to the functions here rather than P itself. It's very standard to pass the address because it's more efficient and is thus faster. Our routines up here, we've got an initialization of the count, which just sets the count value to 0. Now notice that because we're using a structure, the way we access the elements of our structure is via this pointer operation here. So P is the address of our structure. We have created a specific structure here, so it's going to be stored in memory somewhere and have an address somewhere in memory, and the address of P is going to be equal to the address of where the structure is stored. And so if we want to access count that sits inside this structure, we do P pointer, or however you call this thing, count. So our initialization routine simply sets the count to 0 for this particular data structure. So we can already see how I can have more than one counter. I just create P1, P2, P3 and initialize them all separately, and then I can increment them separately. I've got 3 different counters, P1, P2, P3, all lie in different areas of memory. They each have got a count inside them. By accessing the count in this way and this way, I am accessing the data structure in different parts of memory depending on what variable is passed to my routines here. I can therefore maintain any number of counters I like at the same time. The increment's fairly straightforward too. Despite the code being a little bit longer, this is the preferred way of doing things. We can have as many counters as we like. We do not pollute the namespace. Our variables are local. We can initialize counters to different values by easily modifying our initialize count routine. And because we've used a struct, we can add more data that our counter may need to know. Maybe we want a counter that can count both forwards and backwards, or count in steps of 5 or whatever. We can add all these features without any significant change to our program. We just add more data into our struct. Moreover, if we understand how to do it this way in C, then we will understand exactly what MATLAB system objects are doing later. Now we can get back to our block-based processing. We want to add an echo. I'm going to initially do it using global variables because that's the easiest way to understand. So in other words, right now we focus on the block-based processing, but then later we're going to combine our block-based processing with the correct way of using a struct to do it in the nice way. Here is part 1 of our echo. I need to include some standard libraries. My data is going to be stored in global variables, not very elegant, but easy to understand. Here is where I'm going to be storing past data. Remember, to compute the echo, we sometimes need to access past data. Well, this is where it's going to go. We're also going to remember the amplitude and the delay that we want to introduce. Our initialize echo function is relatively straightforward. We pass to it the amplitude and the delay that we want, and we just store it away so that when we call our process function, it knows what amplitude and what delay to use. The only interesting bit is that we now have a buffer that we need to initialize. Because our delay is D, so if this is the current block of numbers that I have to process, because my delay is D, when I come to compute the output for this current input, I need to be able to go back D elements in the past. That means that I need to have a buffer that stores the past D elements so that I can access them. Therefore, my buffer length, it has to be of length D. I need to remember D past data items. The way we do this in C is we do a malloc memory allocation. On the heap, it is going to find some free space. And how many bytes do I need? Well, I need to know how many bytes in a float, and size of float tells me how many bytes I need. Normally I'd expect float to be 32 bits or 4 bytes, but these days, who knows? It might be bigger, it might be smaller. The safe way of doing it is always to use size of here. So doing buff malloc size of float times D is pretty much equivalent to doing float buff of size D. But the difference is you can't write this in C because at compile time you have to know how many elements you want in your array. Here we're doing it dynamically. The other thing is, if I do it the standard way, like this, creating an array, I don't have to worry about freeing up memory afterwards. If I do it using malloc, I should call free once I finished with it, which is why we have a release function down here to free up the buffer once we've finished using our echo. Now, when we create memory, we have to read carefully the malloc function, whether or not it guarantees that the memory it gives us will be initialized to 0. Chances are it might not be. Therefore, I am setting my array to be all 0. Now we need to be a little bit careful because my array contains floating point numbers. I cannot really assume that sticking, so let's assume that float is 4 bytes wide. I have to be careful whether sticking 4 zeros into memory is going to give me a floating point number that is 0. I'm assuming it is, but this is the low-level detail that you need to consider if you're going to be doing this properly. Anyway, the memset function is saying, starting at this memory location, put 0 in there this many times. So in other words, I'm going to take the memory I've allocated and set it all to 0 and hope that by putting all zeros in there, that's going to be recognized as the floating point number 0. If we really did not want to use malloc, and maybe we're running this on a small DSP, and we don't want to use the heap or whatever, the only alternative is to have an upper bound on how long the delay can be and choose buff to be that length. As we said before, because we used malloc, we need to free it later, and that's why there's a release function. In MATLAB, we'll be calling the release function, well, now you know why. It's because you're going to have opened a file or allocated memory, and that needs to be freed up once you're finished. It is the calling program's responsibility to first call init at the start and then call release at the end. But this is a standard programming paradigm, so people know to follow it. If you're interested in learning more about the C functions, well, you can just Google memset, you'll find out all about it. There's also memcopy and memmove that we'll be using later on. Here is our actual echo function that is going to process our data. Because we're using global variables, I don't need to pass in any extra data structures. I can just access them as global variables. I do, however, need to know the same as before. Here is my input block, here is my output block, and this is the size of my block that I will be processing. I simply go through my block one at a time, processing it. I have a case statement, an if statement here, because remember, in the simple case, my output at time I is just my input at time I plus alpha times in at I minus delay. Now, because my echo is time invariant, it doesn't matter whether this is x of k or x of k plus 25 million, it's going to be out of the same value, out of k or out of k plus 25 million. So I don't actually have to know the absolute time at which my data refers. My output is related to my input in this simple way. The output at this time is equal to the input at this same time, plus a delayed version of the input. So that's just I minus the delay here. Now, provided I minus delay is greater or equal to 0, it's going to lie inside my input block, and I've got my delay, the same as before. Very, very easy. The only difficulty is if the delay lies in a previous block and not the current block. In other words, if I minus delay is less than 0, then I need to do something different. In our original echo function, if I minus delay was less than 0, well, that meant that it occurred at time less than 0. And we just assumed that the input was 0 there. But now we're doing block-based processing. I might be up to the 23rd block. And so therefore, I minus delay might refer to something in the 22nd block. But I've been given the 23rd block. I need to access something in the previous block. How do I do it? Well, I will have stored it in my buffer. And how we do that is given down here, and that will be explained later. But the point is, if I need something from the past, it's going to be in my global buffer here, and I can access it like that. Once I've finished my processing of the block, I now need to update my buffer. We will explain more on the next slide, but the way to understand our buffer is like this. Say that I've been processing some numbers, and I'm currently up to processing this block here, and I need to remember some of the past blocks. And the way I understand this is I think of buffer is going to store these numbers, and in is going to store my current block. So if I need to compute the output At this time here, well, I look at the value at the input, that would be this one here, and I also need to know the delayed version of it, which if the delay is 2 will be this value here, and I find that I can access it in this way here to get that value. And we'll see what's happening on the next slide. But once we've finished this processing, what has to happen is everything has to slide to the right. This means that my old buffer here now has to move across, and so 6 and 7 are now going to be in my old buff. And that's what these lines of code do here. But there are two cases to consider. One case is if the size of my buffer is smaller than a block. That's the case that I considered here. Then that's easy. The size of my buffer is just the delay. If it's smaller than the size of my block, then all I have to do is take the last delay elements of my input block and copy them to the buffer. And that's what I'm doing here. The copy is destination, then source. Don't ask me why it's backwards. That's just how C did it. And this is the count. So I'm going to be copying delay bytes, starting at my input buffer, indexed at n minus delay. So in at n minus delay will be this point here. And I'm going to copy, starting here, copying it to here. I end up copying 6 goes to here, 7 goes to here. That's what that one does. If, on the other hand, the delay is longer than the block, that means that I might need to remember the past 4 things, but the size of my input block is only 3. Well, in that case, that means that I need to copy the last 3 things here to the last 3 entries of my buffer, but I also have to have shifted my buffer down first to make room. So that means that this 4 here has to have gone down here to make room for when that occurs. Very messy drawing, sorry, but it just corresponds to sliding the window to the right, which we'll see on the next slide. Some notes. Remember, all we really want to do is calculate y of k equals x of k plus alpha times x of k minus d. And provided that k minus d lies in the current block, we can do that very straightforwardly. In fact, whenever I is greater than or equal to the delay, this will work. It means that this is in the current block and this is in the current block, so we just do this statement here. Otherwise, we need to access data from previous blocks, and that's what this other line does, and it will be explained on the next slide. When we've finished processing the current block, we need to store some of it in our buffer for the next block to use, and that's what these lines of code do. And I just want to point out, for those that care, that memmove and memcopy have a slight difference. Memmove you can use when you're copying data that might end up overlapping. So to elaborate, if I've got an array of data, 1, 2, 3, 4, and I want to copy 3 and 4, I want to copy 2, 3 and 4 to the start of my array. I want to move them across one. Well, you see I'm going to end up with 2, 3 and 4, and there's some overlap here. So if I'm going to be copying data and there's a potential for overlap, it means you have to do the copy in the right order, and then you use memmove. If you can guarantee that in the process of copying there's no overlap, meaning it doesn't matter the order in which you copy the elements, then you can use memcopy, which could be faster than memmove. So to understand block-based processing, we just need to have a simple picture in our minds here. What we want to store is our part of our input sequence, and the first part's going to be stored in our buffer, and that contains data from previous blocks, and the rest of our data contains the current block here. So in 0 is this value here, in of n minus 1 is this value, buffer 0 is that value, and buffer delay minus 1 is that value there. So consider that we want to compute the output for the first input of the current block. So we know that if in0 represents x of k, then buffer delay minus 1, the one just before it, so if this guy is x of k, then the one before it must be x of k minus 1. And the one before that must be x of k minus 2. So because we want yk equals xk plus alpha times x of k minus 2, if that's our delay, we know that the output for the first element of the block is equal to the input for the first element of the block plus alpha times and the first element of our buffer. That's this calculation here. And then the output for the second element is going to be using the second element of the buffer. So you see we've got these two pairs that go together, and these two pairs that go together, then these two pairs that go together. These two pairs lie in the current block, and so we don't have to use our buffer. But drawing a simple diagram will let you see how we are just adding the echo in the usual way. The only difference is our data is not in a single array, we've split it between two arrays. One array is called buff, the other array is called in. It doesn't hold all our data, but it holds a window of our data, and the window is big enough to give us all the information we need to compute the output for that block. The only other calculation we need to do is how to update the buffer. Now, it's important to keep in mind that conceptually this is very straightforward. If I hop back to the previous screen briefly, we see that all we need to do to update things is that once we finish processing the current block, we want to move everything to the right. Our next block is going to be this guy here. Therefore, our next buffer is going to be these values here. So all we need to do is copy 4 and 5 into our buffer, and then we've updated our buffer. Now, this is something that might give you a little bit of a headache. It took me a little bit of a while to make triply sure that I got it correct, so hopefully I did. But the concept's straightforward. So you just need to think of the two different cases. Case 1 is if our buffer is smaller than n, that's the easier way. If the delay is bigger than n, then we need to first move the buffer, shift the buffer across to make room for the block of data, the current block of data to go in there. Conceptually straightforward, you just have to get things to line up and think your way through the logic here that you can read about in your own time. So I'd like to emphasize that that is it. The details might be a little bit annoying. Exactly how to update the buffer in particular is a little bit annoying, but conceptually it's very easy. We just slide everything across when we go to the new block. We're processing things using a sliding window. Now, we've actually covered essentially everything. We just did it in two separate parts. First, we covered how we could pass data around using a struct, and then we discussed how we could process our audio data using blocks. Now we just combine the two. I need 2 slides to write it all, not because it's complicated, just because that's what we need. So at the start, I need to include the standard headers. I'm going to be allocating memory, so I need malloc, and I'm going to be using memset and memcopy, etc. So I need string.h. Here is the data that I need to store for my echo. Same data as before, but it's no longer a global variable. I now store it, I hide it away in a structure, so it becomes a local variable, and I can have as many echoes as I want, operating on different blocks. The data I need to store is the buffer to hold past data, the delay that I want, and the amplitude of the delay that I want. As is standard, I have a routine to initialize my data and a routine to release my data. And people know the programming paradigm. They need to create the data structure. They need to call the initialization routine. They can then use the echo however many times they want, and when they're finished, they release the data block, or precisely the data inside the data block. Our initialization is straightforward. We just store the desired delay, the desired amplitude, we allocate memory for our buffer, and we set it equal to 0. To release it, we just free up the memory that we had allocated for our buffer in here. And here we see our processing code is the same as before. The only difference is we have to pass in the address of our data structure, and when we access it, we use this pointer notation here. This is the only difference to the code. Otherwise, it's identical to before. We're almost finished. In MATLAB, we don't create structs and pass them around like that. There's a nicer way of doing things. We can't do it the nicer way in C. I showed you the nicest way of doing it, the standard way of doing it. In C++, which is an object-oriented language, there is a nicer way of doing it. By nicer, I just mean it's syntactically nicer for the end user. There's actually more code to write for the person creating it. I should point out that although classes are almost synonymous with object-oriented programming, we're just using the basic feature of it. We're not going to talk about inheritance or anything else that comes with object-oriented programming. The key point, though, regardless, is that at the lowest level, what we are doing with classes underneath the hood is identical to using structs. The language is set up to hide the need to pass that pointer, but it is just passing a pointer to a memory location. It's actually the same as before, just hidden away in nicer notation. So this is what it might look like in C++. I can combine, so in C, a struct can only contain data, but in C++, a class can contain both data and functions. And the point is that these functions here have access, immediate access to these variables. Roughly speaking, and don't quote me on this, but roughly speaking, you can think of these variables as being global variables to these functions here, but because these functions are hidden away, then these variables are also hidden away. They aren't really global. But it means that when we program, we can program these functions as if these guys were global data, and that's what we did early on when we took a global variable approach to it, which was perhaps the easiest way of writing the code. So for our C++ class, we can combine variables with functions. These variables act as if they were global to these functions, but they're hidden away, so they're not really global. So we get all the benefits of the structure approach with the convenience that these functions can use these variables as if they were global. The standard way of doing things is you declare the class first and then you declare the functions later. You could declare the functions in the class, but then they might become inline and there are some other issues there, but that's irrelevant for now. So I'm going to declare my initialization function essentially exactly the same as I did before. Rather than using malloc, I used C++ new, but that doesn't matter. And for the release function, rather than using free, I used delete, but again, that does not matter. I want to emphasize this is identical to using structures, just written in a slightly nicer way, due to the power of C++ and object-oriented programming. So some notes. A structure, as we said, can only store variables, but a class can store both variables and functions. And the way we use our class is as follows. Just like I can declare an integer or a float, I can now declare an echo, my whole class. So E1 and E2 are two different echo classes, and I can call their functions on them. E1.init will initialize the first echo. E2.init will initialize the second echo. I can then call E1.process and E2.process to process two different streams of data independently of each other. And then when I'm finished, I release them. So in C code, I'd have to do release, echo, and pass to it the address of E1, for example. Whereas here, I just do E1.release. Under the hood's exactly the same. Here, the notation is a bit nicer. So yes, if you do object-oriented programming, then you'd actually use what's known as constructors and destructors in place of my initialization and release, but I just wanted to make things explicit and to show you that even if you do use constructors and destructors, it's identical to using structs under the hood. I haven't given our echo process function because it's just going to be the same as a block-based echo from before anyway. It's this class thing is just syntactic sugar, makes things look nicer. Perhaps one last thing to explain, because we're going to see it in the MATLAB code. The way I've written my class, I've implicitly made everything public. That means that when I create an echo E, then I have access to its variables. I can change alpha whenever I like just by doing e.alpha equals 23.1. But in terms of safety and so forth, we don't actually want that. And in C, when we declare things, I can have a class echo, and I can start it off by doing private colon. And then when I do float alpha, because alpha is declared under the private keyword, then this will be flagged at compile time as an error. I'm not allowed to access private variables. That means that down here, before I declare my functions, init for example, I need to make them public so they can be accessed by the outside world. I only mention this because a similar feature is available in MATLAB system objects, and knowing what's happening here will make it easier to understand what's happening in MATLAB. Finally, we reach the end. What have we learnt? We've learnt that block-based processing simply requires the ability to store data between function calls. We need some sort of memory because the output at time t might depend on past input, and if that past input isn't in the current block, we must have stored it the previous time or the previous time, etc., when we called our processing function. There's a number of ways we can store this past information. Perhaps the most elegant way is using classes. In C, the next best thing is using structs. It's actually identical under the hoods. It's just a little bit messier to use structs in C. You really want to separate the two things we discussed today. There's the basic algorithm for block-based processing. How do we implement a signal processing algorithm on a block-by-block base? And the answer is because a lot of the algorithms we're doing are going to be time invariant, and they're only going to depend on the finite past. We do it by having a sliding window. We just run a sliding window over our data, and that's it. The other thing that we learnt today was the actual programming techniques that allow us to do this. And this is just a programming aspect, nothing to do with signal processing as such. And we saw that we can do it the nice way using either structs or class. Part 2 is going to look at MATLAB system objects and explain how to use them. Then part 3 will look at how to implement a flanger in MATLAB.